Well, thank you very much. It's a pleasure to be here. I hope I'm still welcome, even though I'm from a Department of Energy National Laboratory. DOE took kind of a thrashing this afternoon at lunchtime, so I thought maybe I'd steal 30 seconds and remind you all about something that hopefully is non-controversial about the DOE. DOE pumps in about $5 billion into basic science research every year, which in addition to the NSF's $7 billion or so constitutes the full funding for basic R&D into fundamental non-defense research in this country for particle physics, nuclear physics, basic material science, chemistry. It runs the largest collection of scientific user facilities on the planet. 6 light sources, the world's first X-ray laser, the most capable neutron source on the planet, and 40 miles from here is the premier particle physics laboratory in the United States, one of 2 premier laboratories on the planet that focuses solely on particle physics. So Fermilab does in fact have a future, and I'm going to describe our future, and one very interesting aspect of that future is the potential and the real synergy that our future in particle physics has with helping to solve some of the real problems that we face from the standpoint of energy. So I'm going to switch gears now and talk about accelerators and what particle accelerators have to do with energy, and in particular have to do with thorium energy. So we've talked about the challenges. Previous speakers have outlined what we're up against. Previous speakers have summarized the advantages of thorium. So I'm not going to go into those. They've been well summarized earlier. But when it comes to deploying thorium, there are different approaches. Different communities are taking different directions in deploying thorium energy. So we've heard a lot about molten-salt reactors, thorium in terms of liquid fuel and molten-salt reactors. There's thorium fuel in solid form in conventional reactors. And there's sort of a third stream, and this is really my focus on this presentation, and that is deploying thorium energy with particle accelerators. So the notion here is to build specialized reactors that are subcritical, they're not capable of reaching criticality, and to supply missing neutrons, so to speak, generated with a particle accelerator. So this is a notion that has taken the name energy amplifier that's attributed to Carlo Rubbia, but the concepts and ideas have existed for quite a while. So let me jump ahead to the elements of an accelerator-driven subcritical reactor system. There are 3 pieces that we're talking about, 2 of which you don't find in lifters or in conventional reactors, so it's worth understanding what's special about those. First of all, we need a high-power, very reliable proton accelerator. This is a proton accelerator capable of producing beams in the 1 billion electron volt range in energy, producing megawatts of beam power. For a demonstration facility, you would like something of the order of 1 megawatt of power actually contained in the proton beam itself. For an industrial scale system, we need accelerators capable of sort of 10 megawatts of beam power. The beam from that linear accelerator or some other type of accelerator technology is directed to a spallation neutron target. Spallation is a tremendously useful reaction for protons in the GeV energy range. For every incident proton, about 25 fast neutrons are produced when that proton strikes a heavy metal target. So these protons, in fact, provide an external source of neutrons that have an on-off switch, literally with the on-off switch of the particle accelerator, that delivers neutrons to the core or turns off the delivery of neutrons to the core. Why would you want to do that? Well, the whole point is to design a reactor that is physically incapable of reaching criticality. So the core is designed to remain subcritical in all conditions. It's not capable of reaching criticality by design. The chain reaction, in fact, is therefore sustained by this external neutron source and can be turned on and off as the accelerator and the source of neutrons is turned on and off. You can think of this system as an energy amplifier. With a high energy, high current proton accelerator delivering In this particular case, the numbers I have here are a case of a 13 megawatt proton accelerator. So the power delivered in that beam of protons is 13 megawatts. It's directed into a spallation target embedded in the core of a subcritical reactor. That generates about 1.6 gigawatts of thermal power. We need about 20 to 30 megawatts to run the particle accelerator. So with an energy extraction efficiency of, let's say, 40%, that puts about 600 megawatts of power on the grid. So it's an amplifier in the sense that you supply beam power and you get thermal power out that can be put on the grid or can be used for process heat. So what are applications of accelerator-driven systems? They actually came about long before thorium. They came about right after World War II for producing isotopes that are important for weapons. So the notion of using accelerators to make isotopes has been around almost as long as accelerators have been around. So what are the applications of this sort of technology? Well, there's several things. Transmuting selected isotopes that are present in nuclear waste, that is using an ADS system as a nuclear waste incinerator. Generating electricity in a thorium fuel cycle, as we've heard about all day, or maybe just generating process heat for use for some other function, or producing fissile materials that are subsequently used in critical or subcritical systems by irradiating fertile elements. So for instance, you could start out with a pure thorium blanket and breed uranium-233 as we've heard about earlier today. So why do this? Why bring accelerators into the picture? Systems are complicated enough. Why the additional complication of adding a particle accelerator? Well, there are at least 4 reasons, and depending on the mission and the application, some of these reasons are more or less important. One very important reason, and one of the early speakers today mentioned this right off the bat, that the problems we're facing are not necessarily technical problems, they're political problems. A system in which the core is subcritical and cannot reach criticality adds yet another layer of inherent safety to the entire system. The external neutron source is eliminated when the beam is terminated. The core is subcritical, therefore we are not capable of reaching criticality or having a runaway condition. There's greater flexibility with respect to fuel composition. From the technical standpoint, I think this is the strongest reason for bringing accelerators to the table. These accelerator-driven systems can burn fuels which you would not choose to burn in a critical system. These are fuels that have poor neutronic properties, they have poor delayed neutron fractions, they may have poor delayed neutron lifetimes. An example is pure minor actinide fuel. If we want to incinerate pure minor actinide fuel, an ADS is a perfect place to do that because we can do it safely independent of the poor neutronic characteristics of a core and fuel assembly that is constructed with minor actinide fuel. It can burn up isotopes from spent nuclear fuel, as I mentioned, including minor actinides and plutonium. In fact, one of these ADS reactors can serve a dual function as an energy amplifier generating power to the grid, or it can be operating in a mode where its function really is for incinerating and burning waste from spent nuclear fuel. ADS allows the use of non-fissile fuels. You could, in fact, run an ADS with pure thorium without the incorporation of uranium or plutonium fissile material into fresh fuel. So you could, in principle, start up a system with pure thorium. Takes a while to build up U-233, but then at that point, you're off and running. Changes in reactivity can even be compensated with accelerator beam power. So as the reactivity changes over the lifetime of the fuel, that can be compensated by turning up or lowering the accelerator beam power. So what are we talking about in terms of beam power requirements, and how do these power requirements compare to the sort of accelerators that we've built? Well, it depends on the level of subcriticality. What's plotted here are curves of the particle accelerator beam power measured in megawatts needed to drive a 0.8 gigawatt blanket as a function of proton beam energy, and 3 curves correspond to 3 different effective neutron multiplication factors. So For a neutron multiplication factor of 1, you don't need a particle accelerator, and that's a critical reactor. When the multiplication factor is brought below 1, you need an accelerator to generate an external source of neutrons to keep the reaction running. As you get closer to 1.0, the beam power required is less and less and less. So folks have been focusing attention on subcriticality of 2 to 5%, so somewhere between this green and blue line, probably closer to the green. So that means for 1 billion electron volt protons, you need about 7 megawatts of proton beam power in such a system to generate 0.8 gigawatts of thermal power in a blanket. So what are the requirements and challenges for these sorts of accelerators? Do they exist? Have they been built? What's the state of the art? Well, we need proton beam energy in the GeV range. GeV is perfect for the production of spallation neutrons. The energy is very well matched to subcritical core design. It's sort of a normal-sized core. If we go up to much higher energy, we have to enlarge the size of the spallation target and shielding, and the system can become unwieldy. It minimizes capital costs because 1 GeV is not a particularly high energy range for a particle accelerator. But we do need very high beam powers. For industrial scale systems, we think we need powers in the range of 10 to 20 megawatts. High power is required for industrial systems to justify the capital expense. The goal, of course, is to keep the cost of the accelerator well below the cost of the subcritical reactor itself. There are various technical complications in terms of designing, building, operating a particle accelerator that has extremely low beam loss. Very small fractions of the beam are allowed to be lost as that beam is accelerated down the accelerator chain and transported to the beam line. That's for activation reasons, to be able to perform routine maintenance on such a system. We have to accommodate very high deposited power densities in the target, something like 1 megawatt per liter in a liquid target, which is achievable but high. Beam trip frequency has to be minimized. The accelerator cannot be tripping off accidentally all the time. It needs to have a very high level of reliability. And the overall availability, of course, if it's not up to the standards of modern nuclear power plants, it's not very useful. So, what accelerator technologies are out there that we can look at? Well, folks look at cyclotrons. Cyclotrons sort of look like this. This is 80-year-old technology. Been around for a long time, but it's been continually improved over the years. People look at synchrotrons. This is now sort of 40 to 50-year-old technology. It's been improved a lot over the years. There are various pros and cons in each of these approaches. I think it's fair to say most people are focusing on types of accelerators known as linear particle accelerators. These are accelerators that, depending on your point of view, were sort of born in the 1970s, and I think reborn in the mid-2000s, just about 10 years ago, in this accelerator, which is in Oak Ridge, Tennessee, called the spallation neutron source, which is in many ways a prototype of a particle accelerator that would serve the job for accelerator-driven systems. It's based on superconducting radio frequency technology, a very specialized technology that has a number of technical benefits. It can produce very high average current and therefore very high average powers. It's perfect in the range of 1 GeV, even 2, 3. You'll see our plans at Fermilab call for a very high energy LINAC of this variety. I also need to point out there are new technologies being explored as we speak. In particular, there are groups in the UK and Japan who are very actively pursuing a type of synchrotron technology known as a fixed field alternating gradient synchrotron. Has attractive features, but it's at the prototyping stage, so one wouldn't want to stand up and say that we can build this machine right now. So most of the emphasis has really been on linear accelerators. So, do we have any history with this stuff? Well, as I mentioned, the history of these high-power proton accelerators goes back to the 1950s. This is the first example of an attempt to build one of these high-power accelerators. This was at the University of California Radiation Lab. It's a giant, humongous accelerator. You can literally drive a truck through. There are train tracks through this thing. We got a lot smarter, and in the early 70s, built at Los Alamos, the Lance LINAC. It's a nearly 1 GeV normal conducting proton LINAC that has delivered 1 megawatt of beam power. The cyclotron technology has been pushed to its limits in a laboratory in Switzerland at the Paul Scherrer Institute. This machine produces 1.4 megawatts of beam power. Synchrotron technology has been pushed to its limits in a number of places. This is at Rutherford Appleton Lab in the UK that operates a synchrotron at about 0.2 megawatts. Fermilab's large synchrotron, the main injector, operates a beam power of about 0.4 megawatts, but at very high energy. And the spallation neutron source in Oak Ridge operates a beam power of more than 1 megawatt, and as I said, in many ways is sort of a prototypical example of an accelerator-driven system. Our plans at Fermilab focus on an accelerator called Project X, which I will describe in a moment, which takes the state-of-the-art established at the spallation neutron source and extends it even further. We carried out, I should point out, under the auspices of the Department of Energy, a technology assessment of accelerator-driven systems technology. So we put a team together to answer the question of what has happened with this technology in the last 2 decades. Has it advanced? Is it to the point where one can imagine actually deploying it in the nuclear fuel cycle? We had a very sophisticated green, yellow, and red scheme of scoring, and I'm not going to go over all these different categories, but you see from the standpoint of demonstrating this technology, we conclude we're ready to go. There are no showstoppers. From the standpoint of building an industrial scale system right now, we conclude we need work on reliability, but the technical components are there. So the next natural step is, in fact, to demonstrate this stuff. Europe has made a commitment to, in fact, demonstrate an accelerator-driven system. So the Nuclear Research Laboratory in Mol, Belgium, is putting together plans as we speak for a demonstration facility called MIRA that will be the world's first high-power coupling of a high-power proton accelerator and a subcritical assembly to demonstrate this technology, and at the same time to build a very powerful materials irradiation facility. So Fermilab's plans center on a new accelerator known as Project X. So for those of you who don't know, Fermilab's located about 40 miles west of here. It has a rather large complex of, depending on how you count, of order 8 particle accelerators that take protons from very low energy up to very, very high energies. We do all sorts of crazy things like create beams of neutrinos that shoot under the earth and emerge in a mine in Minnesota where we measure the properties of neutrinos and how they've morphed from one flavor to another throughout that path. We do a lot of work right here on the site. We have plans to take the state-of-the-art in linear accelerators to the next level with a project that we call Project X. Project X is an accelerator that will deliver 3 megawatts of beam power at 3 GeV. So this is just the sort of beam power you need in just the sort of format to be able to demonstrate this accelerator-driven system technology at high beam power with prototypic conditions in a way that is a clear stepping stone to where we need to get in deploying thorium energy based on accelerators. Of course, our mission in life is particle physics. So the Department of Energy funds Fermilab to do particle physics research. But it so happens that that accelerator we need to build for particle physics is just the sort of accelerator you would want to build for ADS. So therefore, it opens up a lot of possibilities for proving concepts, proving ideas, and serving as a test bed for the development and deployment of this technology. So, a demonstration facility coupling a subcritical assembly to a high-power accelerator needs this 1 to 2 megawatts of beam power in the GeV range. That's exactly what we intend to build. This 3 GeV continuous wave proton beam delivered from Project X has many of the elements that are prototypical of an accelerator-driven system. There's a lot of effort that we're putting into and collaborating with other laboratories, collaborating with our sister lab, Argonne National Lab, which is right here in the Chicago area, as well as Pacific Northwest National Lab, on materials irradiation, on target system and subcritical assembly studies, demonstration of transmutation technologies, and then on the accelerator end, we're putting a lot of emphasis and effort onto the reliability of components. So finally, we're all here because thorium holds real promise as a game changer. There are a lot of advantages we've heard about all day, but we need to recognize, and the world surely recognizes, the potential that particle accelerators can play in the fuel cycle, and in particular in deploying thorium energy. We believe the case has become much, much stronger in the last decade thanks to a number of technological advances that have taken place mostly in the United States, I have to point out, in the national lab system in developing these very advanced accelerator technologies. And as has been pointed out earlier, the rest of the world notices that. Europe is building a demonstration facility. India has committed to developing and deploying accelerator-driven systems as part of their nuclear strategy. China has committed to building an accelerator-driven system in 2 decades that will drive a 1 gigawatt blanket with a 15 megawatt proton particle accelerator. So they have set a goal for themselves 2 decades out by 2032 of building an industrial scale system. So it's time for us to get on board and not miss that train, especially since most of this technology was actually developed right here in the United States. So Fermilab's next accelerator, Project X, is ideally suited to develop and demonstrate this technology, and many of us feel that accelerator-driven thorium reactors may, in fact, well be the future of nuclear energy.
Does China have the accelerator?
No. China is bootstrapping their accelerator development program by setting some intermediate targets. So their nearest term intermediate target is to build a spallation neutron source, which in many ways is similar to Rutherford Appleton Laboratories' spallation neutron source. It's based on a synchrotron running at a few hundred kilowatts. So in fact, that's a project under construction now. They've broken ground on that. So they've set these waypoints to first get into the business of high-power proton accelerators, secondly, to get into the business of superconducting radio frequency accelerators, which is a special technology I didn't spend much time on, but which really is the technology to carry out ADS. And in this, you know how it'll work. They'll set these goals and leapfrog from one to the next over the next 2 decades.
The presentation was all about the accelerator, which is just a few % of the neutrons needed for criticality. I didn't hear anything in there about fuel form, coolant, power conversion system, all the rest of the reactor stuff. So, and frankly, we don't need an accelerator to make a critical thorium fuel cycle reactor. So help me understand, where's the rest of the reactor in this?
The rest of the reactor is in many ways what's been discussed all day today. So the real question is, why bring an accelerator into it at all? Which is what I tried to address early on. So there's flexibility with respect to fuels. That's number one. In fact, some in the US would argue that the killer app for ADS is waste incineration and transmutation.
It does minor actinides. One of the points of the thorium cycle is not to produce minor actinides.
No, I understand that. I'm just saying that when we look at applications of ADS, there are several that I laid out, and some in this country feel like the real killer app for ADS, based on where we are now, is in dealing with the waste problem. However, there are others who argue very strongly that for political and societal acceptance reasons, running a subcritical system is the only way you're going to get nuclear power taking off again. That would be perhaps a European point of view pushed, not so much in this country, but in Europe.
The amount of money that the DOE is spending on this could be used to build a lifter or a molten salt reactor that could handle nuclear waste and prove that to the public, and we could circumvent all this and get our neutrons from fissile fuel.
The DOE is not spending a penny on ADS.
Okay, well then whoever's spending the money on it.
That's sort of the point. In the United States, we don't have an ADS program, so the DOE does not fund it. DOE funds particle physics, nuclear physics, basic material science. We don't have an ADS program in this country. Europe does, India does, China does, US does.
I apologize, the echo in the room, I might have missed a few critical words in your speech, I apologize.
Thank you, Stuart. Thank you so much for coming here.